It's called differential equations of equilibrium for planar loading. We will quickly go through the derivation and then we can discuss the applications. Now, if you consider any beam subjected to any distributed loading Wx, and you consider a small segment of dx length, and you consider free body diagram of that segment, then you will have some loading on this side, and then you will have certain moment. We are considering m and v to be the value of moment and shear at this location to be m and v, and on going on this side there will be certain change, and on going on this side there will be also a certain change in the values of the bending moment and shear force, and that's why we can see change in the moment values as you go on this side and as you go on the other side. Similarly for the shear force. So if you consider summation of vertical forces for this segment, you end up equation like this. And if you combine the similar terms, you will see you can write down df. And when you just open this up, you will see that some of the terms could be cancelled out and some of them could be combined, like dv by dx into dx by 2, and then also you will have plus dv by dx into dx by 2, so that will become dv by dx times dx, and then you can cancel, take this dx term common. Doing some basic mathematics, you can reach this answer, get this expression, and because you can see that uh, mathematically you can say that either this term is 0, this first term, or the second term must be 0. So the second term should not be 0 because we have considered a certain length which is not 0. We have considered a certain non-zero length. So dx should not be 0 and this term must be 0. So dv by dx should be is equal to w. This is one equation. In words, we can say that the rate of change of the shear force is equal to the applied distributed loading. Just keep in mind that we have taken the load downward. जो भी हम derivations के अंदर force की direction या किसी चीज़ की direction show करते हैं, वो उसकी positive direction होती है. या दूसरे अल्फाज में आप कह सकते हैं कि derivation में हमेशा उस किसी भी चीज़ की सिर्फ positive direction show की जाती है, क्योंकि उसमें कोई numerical values होती नहीं, सिर्फ जब हमने सिर्फ सैम्पल्स यूज़ करने होते हैं तो इसलिए हम इसमें सिर्फ जो भी वेरिएबल शो करेंगे वो उसके पॉजिटिव डायरेक्शन में शो करेंगे. या अगर हमें किसी की वेरिएबल के पॉजिटिव डायरेक्शन का नहीं पता, तो जो हमने साइन कर जो डायरेक्शन हमें उसकी डेरिवेशन में शो कर दी है, वही जब हम न्यूमेरिकल सॉल्व करेंगे तो वही डायरेक्शन उसके पॉजिटिव कंसिडर की जाएगी जो डेरिवेशन में दिखाई गई थी. तो लोड को हमने डाउनवर्ड पॉजिटिव लिया. उसकी वजह यह है कि जो often these are loads are due to gravity, and gravity is directly downward, so that's why we are taking these forces. The loads को हम downward positive ले रहे हैं. आमतौर पे जो पॉजिटिव का वर्ड है ना, पॉजिटिव, किस चीज़ को पॉजिटिव लेना है, किस चीज़ को नेगेटिव लेना है, आमतौर पे पॉजिटिव उस चीज़ को लिया जाता है. यानी मैं आपको जनरल प्रिंसिपल बता रहा हूँ, जनरल गाइडलाइन बता रहा हूँ कि साइन कन्वेंशन के हवाले से जनरल गाइडलाइन ये है कि आप पॉजिटिव उस चीज़ को लेते हैं जो रूटीन की चीज़ हो, जो ज़्यादा कॉमन बात हो. ठीक, ये नेगेटिव उस चीज़ को लिए जाता है जो आप कहते हैं ना, ये नेगेटिव आ गई, अच्छा ये तो रूटीन से हट के कोई वैल्यू आ गई, समथिंग डिफरेंट फ्रॉम व्हाट यू वर एक्सपेक्टिंग. So loads are usually expected to be downward, so we consider them downward positive. This makes sense. I have seen some books which use loads, which consider loads upward positive for the same derivation. But I think this is a better approach to consider the loads to be downward positive, because loads often are directed downward. All right. So बाकी shear और moment की convention वही है जो हम पहले discuss कर चुके हैं, sign convention. So this means that the slope of the shear force diagram is equal to the intensity of loading. So at any point, the slope of shear force diagram is equal to intensity of loading at that point. Next, if you repeat the same analysis for this equilibrium, for this free body diagram, if you consider summation of moments for this segment, you can write this expression, and I'm doing some simple calculations, you can reach this answer, and then again you can say that this term should not be 0, rather the first term should be 0. So this term is equal to 0, and that can be rearranged to say dm by dx equal to minus v. Dm by dx equal to minus v. So you could describe this equation as to say that the rate of change of the bending moment is equal to minus times the shear force, or you can say the slope of the bending moment diagram at any point is equal to negative times the ordinate of the shear force at that point. Now these two relations are quite useful for checking the shear and bending moment diagrams at a glance. So what these equations really tell you, जिस तरह के अगर एक बीम के ऊपर लोड लग रहा हो इस तरह से और इस तरह से, अब अगर आप ये वाला सेगमेंट देखें, कोई भी सेगमेंट बीच में ये वाला सेगमेंट, अब इस सेगमेंट में W इज़ ज़ीरो, इसको मतलब है इस सेगमेंट के अंदर, या आप इस सेगमेंट को भी ले सकते हैं पूरे बड़े सेगमेंट को भी, लेकिन जस्ट टू एक्सप्लेन दिस मैंने ये छोटा सेगमेंट कंसिडर कर दिया। इसका मतलब इस रीजन के अंदर, इस रीजन में द shear force will be a constant value, ठीक है, will be a constant value shear force, और bending moment will be, अगर ये reference line है, bending moment will vary linearly, maybe this way or this way, whichever way, ऐसे भी वेरी कर सकता है, मैं जस्ट ऐसे लाइक लाइन शो कर रहा हूँ, ठीक है, ऐसे करके वेरी कर रहा होगा, maybe this way. So this is how you need to interpret these equations. Let me remove these because now next is that we have something like this, uniformly distributed load. Now in this again, if you consider certain segment, maybe this segment, then you can see that W is a constant value in this case. It means that dV by dx will not be zero, it will be a constant value. So there will be some slope of the shear force, but it will be a constant slope. That means that that means that dV by dx will vary somewhat like this. It will be a straight line. Constant straight line की slope constant होती है ना, इस line की slope constant भी है और zero भी है, ये भी constant line की slope है लेकिन zero है, जैसे हमने ऊपर देखी थी ये वाली line, this was a constant slope, but and constant में से भी ये zero slope था, ठीक, और ये constant है लेकिन non zero slope है, ठीक है, या rise करेगा या फॉल करेगा। और फिर बेंडिंग मोमेंट डायग्राम के केस में अगर हम देखेंगे, सो इफ dv by dx इज अ कांस्टेंट, तो अच्छा अगर ये कांस्टेंट होगा तो आप देख सकते हैं कि बेंडिंग मोमेंट डायग्राम को क्या होगा कि now the values of shear will vary as you go along this segment. It means that dm by dx, this will vary. This V is this varies along the segment. It means the slope of the bending moment diagram will vary. Vary कैसे कर सकते हैं? It will be a higher order, second order equations, quadratic equation, ठीक है? Something like this. Maybe. Or maybe like this. Okay? So this is what these equations mean. This is how you will use these equations. Plus इसमें ये भी होगा कि if I can. Okay, we will discuss them in the numerical problems, so better to discuss them in a real example. Okay, now this is one way to write these equations. One way, is to write them in differential form like this, as you can see over here, these two equations. The other way is if we consider a segment of the beam between 2 points x1 and x2, and you integrate these equations between x1 and x2. All right. So if you consider a segment of the beam between x1 and x2 and you integrate, for example, this equation, you will see that by integrating this equation, write it as v2 minus v1 equal to integral of w dx between x1 and x2. So if you integrate it between x1 and x2, you can see this is delta v change in shear equal to in fact, if this is equal to integral of w dx between x1 and x2. Okay, so you can rewrite this as, and this can be rearranged to say v2 equal to v1 plus integral w dx x1. And then for the other equation, again, if you integrate, this can be written as m2 minus m1 equal to, okay, you can stop writing it this way because I mean you can always rearrange it whenever you like to. It's better to keep it in this form, mine equal to minus integral v dx between x1 and x2. And these are the differential equations of these are the same equations written in integral form. These are again very useful. You can see that this equation says that the difference between two values of shear at x1 and x2, v2 minus v1, the difference between two values of shear is equal to the area of the load diagram between those 2 points. All right, so if you have, so if you were considering points x1 and x2, then the difference between v2 and v1 would be equal to the area of the distributed load between these 2 points. So if this is the distributed load and then this is the area under this distributed load, and then v2 is equal to v1 plus area of the distributed load. So if you know v1, you can obtain v2 by adding area of the distributed load to this v1. Keep in mind that we are considering distributed load positive downward. So this, if this is a downward distributed load, if it is acting downward, if this load is acting downward, so this area of the distributed load will be a positive value because we are considering downward load positive. Similarly, the other equation says that the difference between 2 points of the difference between m2 and m1 is equal to negative times the area of the shear diagram between those 2 points. So you just need to know the area of the shear diagram between these 2 points, and you can know the difference between m2 and m1 by just changing the sign of that area. If this is a positive coordinate, this will ultimately become a negative answer. So it depends upon the area. We will see the applications in a while. Points of maximum shear, maximum moment. If we are interested in locating the values of the maximum bending moment, the values of the maximum bending moment, what we can do is you can use the concept of extreme values. You can use the you know that if you have any function, if y is a function of x, then if you want to locate the maxima and minima of this point, this y, what you can do is you can derivate this y and put the derivative equal to 0. It means you will be able to locate the points where slope of this function becomes equal to 0. So by locating those values, let's call those values of x to be x steric equal to 0. X steric some value. So when you put the when you evaluate this function at x equal to x steric, you will get either a local maximum or a local minimum. This is what the mathematical concept is. So based on this analogy, if we have if we find the derivative of moment and put it equal to 0. Now this derivative is equal to minus v, and that means if you put minus v equal to 0, that means also putting v equal to 0, because minus v equal to 0 means v equal to 0. If you can just multiply both sides by minus 1, then and find the value of x from this equation. Let's call that value of x as x static. This v would be a function of x, keep in mind. This v will also be a function of x. M and v both are functions of x, just as this y is a function of x, so its derivative will also be a function of x. Alright, you can understand these things. This will be a certain value, whatever you get. And then if you find m at x equal to x static, this will be either a local maximum or a local minimum. This is how you can locate the maximum and maximum positive values. So you would say that this will be either a maximum, this will be either a positive maximum or a negative maximum. Maximum on the positive side or on the negative side. You can end up any value. Okay, so this is how you can locate the points of maximum bending moment. Okay, now if you wanted to locate yeah, that's right. So these were the equations if load is uniformly distributed. If load is uniformly distributed, then you can use these equations. But if we have a situation like this, so if we have a concentrated load or a couple acting, how do you handle them? How do you find a change in shear in that case? You would know that when the loading consists of concentrated forces, shear force diagram has a jump at the point of application of each concentrated force. So if you consider now if you consider a beam with concentrated load and you consider that particular segment in which the concentrated load is present, so in that case you can see that V on the negative phase and V on the positive phase can be related by this expression. V on the positive phase minus, if you can just consider the equilibrium for this three-body diagram, then V on the positive phase minus V on the negative phase would be equal to P. The difference between V of the positive phase and V on the negative phase would be equal to P. So this V and this V negative differ by a value of P. The difference between them would be equal to P. So if you wanted to, you can use them in any case. If you know the V positive, you can use it to calculate V negative. If you know the V negative, you can use it to calculate V positive phase. Similarly, if you have a concentrated moment, and that's something we call a couple moment. If a couple moment is acting over here, or externally applied moment is acting at this point, and you consider a segment just around this point, then M on the negative phase and M on the positive phase are related by this expression. M on the positive phase minus M on the negative phase is equal to minus M. The change in between these two forces, these two, is equal to minus M. So if you wanted to find, if you know M negative phase, you can use it to calculate M positive phase, and if you know M positive phase, you can use it to calculate M negative phase by just either adding or subtracting this M value depending upon your case. So let's now apply these concepts. Let me just write these things down for you and then we can discuss them. So V on the positive phase minus V on the negative face equal P. Now keep in mind that we are considering P downward again positive. P is downward, P is considered positive again. Alright, so a downward value will be considered positive and a negative upward value will be considered negative. Again, we expect that loads are applied downward usually, so we consider the downward value positive. Similarly, if you look at this equations, you can again say that M positive phase minus M negative phase is equal to minus M. Okay. So these are not just random difference. So you must write this in the same format as you can see. It is V positive phase minus V negative phase equal to P. So you should write it in exact this format. You shouldn't rewrite it like V negative phase minus V positive phase, because this equation is actually V positive phase minus V negative phase equal to P. And similarly, this equation should be written in the way it is written. Okay, so now let's go on to the numerical problems.